In this video, we're going to look at another instance of the hidden subgroup problem, which is the discrete logarithm problem. Now, Shor also gave a quantum algorithm for the discrete logarithm problem in his famous paper that gave the algorithm for integer factorization. And the algorithm for the discrete logarithm problem, I would say, is actually easier than the algorithm for integer factorization, especially the classical post-processing part is much easier. So let's take a look at this problem. So what is the discrete logarithm problem? Okay, so in the discrete logarithm problem, we have some group. Actually, I didn't write it here, but we start off with some group, let's say H, and we take some G in H, and we look at the cyclic subgroup G, which is generated by little g, okay? And now I'm going to write things multiplicatively. So this cyclic subgroup G is just going to be all the powers of G, right? 1g, g squared, etc. And if we suppose that capital N here is the least positive number such that g to the n is equal to 1, this is also known as the order of G, then our group here is going to have n many elements, okay? So we don't include g to the power n here as well because, well, that's just equal to 1, okay? So now we're just going to work in this cyclic subgroup G, capital G. Okay, so in the discrete logarithm problem, we're given some x, which is in G, so it is some power of little g. And the question is to find the least non-negative a such that x is equal to g to the a. Okay, so we know that x is some power of g. We want to find out which power. And just like you're familiar with logarithms over the real numbers, we're going to denote this power a such that g to the a is equal to x as the log base g of x. Okay, and that is our problem. We want to find, we're given x, we know little g, and we want to find the log base g of x. Okay, so let's look at an example. So let's look at the operation of multiplication modulo 11. Okay, and let's consider the subgroup generated by 7. Okay, so we just look at powers of 7 modulo 11. Okay, so here I've written all of them out. Okay, and you see that we actually get everything here in the integers modulo 11 except for 0. Okay, so every element in Z11 that has a multiplicative inverse is some power of 7. Okay, so this is just known as the multiplicative group modulo 11 and denoted like this, which I'm going to read as Z11 times. Okay. Okay, so now that we've written everything out, we can use this to figure out some discrete logarithms. Okay, so what is the log base 7 of 10? Well, we see here that 7 to the power 5 is equal to 10 modulo 11. Okay, so so this log base 7 of 10 is 5. And log base 7 of 6, so what power of 7 is equal to 6? So here that we see here that 7 to the power 7 is congruent to 6 modulo 11. Okay, so so the log base 7 of 6 is 7. Okay, so here's one for you. What is the log base 7 of 1? Okay, so this is meant to be a little bit of a trick question because your eye may catch this one here, that 7 to the power 10 is equal to 1 modulo 11, but of course also 7 to the 0 is equal to 1 modulo 11. Okay, so, and we're looking for the least non-negative a, such that 7 to that power a is equal to 1, so this would just be 0. Okay, so this is to get you more familiar with the discrete logarithms. And now to give you a bit of a flavor of the computational complexity of discrete logarithms, let's look at a bigger group here. So let's look at a group um, of units modulo 163. Okay, so what is the log base 18 of 65? This is just to give you a sense of, it's not at all obvious what this should be. Okay, this is not an easy problem, but now imagine that I just tell you what the answer is. Okay, so I just tell you that 18 to the power 132 is equal to 65 modulo 163. Okay, so I claim that if I actually tell you this, it's actually quite easy for you to check that it's true. Okay, now why is that? Well, we can just compute the powers of 18. We can compute 18 raised to powers of 2. Okay, so modulo 163. Okay, so here I have 18 to the 1, 18 squared, 18 to the power 4, 18 to the power 8, okay, etc. Okay, so I only have to look at, something like the logarithm of 163, the log base 2 of 163, many exponents here. And now from this little chart, I can actually compute 18 raised to any power modulo 163. Okay, so how does that work? Let's look at this example. Okay, so in this case, we want to compute 18 to the power 132. So we just, consider the binary representation of 132. Okay, so 182 is just 128 plus 4. Okay, and now we know from this little chart what 18 to the 128 mod 163 is. That's 57. And we know what 18 to the power 4 is, modulo 163, so that's 4. And that lets us compute 18 to the 132, right? Because 18 to the 132 is just going to be 18 to the 128 times 18 to the 4, or 18 to the 128 mod 163 times 18 to the power 4 modulo 163. Okay. So we know those values from our chart, and then this 57 times 4 modulo 163, then we can compute quite easily. And we see that the answer is indeed 65 as we wanted. Okay, so this is just to give you an intuitive feel that discrete logarithm is a problem that seems kind of hard. It's kind of hard to figure out what is the log base 18 of 65. But if someone tells you the answer, then it's actually pretty easy to check that that answer is correct. The complexity is something just on the order of the logarithm of the size of the group that we're working in here. Okay, so indeed, we do currently think that the discrete logarithm problem is a hard problem classically. And the best heuristic algorithms that we know of, so algorithms, assuming some number theoretic conjectures, over ZP times take time roughly exponential in the logarithm of p to the power 1/3. Okay, so this is basically similar to the running time of the best heuristic factoring algorithms that we know of. And indeed, there is a close connection between the discrete logarithm problem and factoring. So it was known quite early on, so in the 70s and 80s, that if you can solve discrete logs, then you can factor. And this is actually where the kind of classical reduction part of Shor's algorithm comes from, right? The way that this was shown was by showing that you can use the discrete logarithm to compute the order of a random x in Zn times, okay, which is of course also a fact that Shor's algorithm is taking relies on to factor in. So although there is this close connection between the discrete logarithm problem and factoring, And the analysis of Shor's discrete logarithm algorithm, I would say, is much easier than that of his factoring algorithm. His discrete log algorithm does not suffice to give his factoring result. And the reason why is that Shor's discrete logarithm algorithm assumes that you know the order of this cyclic subgroup that you're working in, okay? And in the case of the multiplicative group modulo n, the order of this group is actually the number of numbers that are co-prime to n, which is known as the totient function, phi of n. And computing this number is known to be as hard as factoring itself. Okay, so just to give you some more familiarity with discrete logarithms, I want to talk about a really nice protocol based on discrete logarithms for two parties to share a secret key. And this is called Diffie-Hellman key exchange. Okay, so Alice and Bob agree on a prime number p and a generator for ZP times. Okay, this multiplicative group modulo p. So I'm going to stick with using modulus 163, and as a generator, let's just take g equals 2. Okay, then Alice randomly chooses a number between 1 and p minus 1, and Bob does the same thing. Okay, and now Alice computes g to the power a. A is this, again, this random number that she chose. So she computes g to the a modulo p. Now remember, again, this is something that's easy to do. So she computes that and she sends it to Bob. And Bob does the same thing. So he raises g to the random number b that he chose, modulo p, and he sends that number to Alice. Okay? And so Alice receives B, capital B, from Bob, and then she raises that to her secret. So she raises that to the power A modulo P. Okay, and again, this is something that's easy for Alice to do, right? And Bob does the same thing. So he takes the value that he received from Alice, capital A, and he raises it to his secret value, B, okay, modulo P. And now the very cool thing is that, of course, B, capital B to the A mod P is equal to capital A to the little b mod P. Okay, right? So they're both just equal to G to the power A times B modulo P. Okay, so now Alice and Bob, share the same number. Okay, so now why do we think that this number is secret? Right? So let's think about what is known publicly. So what's publicly known is G and P, and then Alice's message, which is G to the power A mod P, and Bob's message, which is G to the B mod P. Okay? So now if you could compute discrete logs, then from seeing Alice's message, you could compute A, and from seeing Bob's message, you could compute B, and then since you know G, you could just yourself compute G to the power A times B. Okay? And this is still the best way we know how to break the Diffie-Hellman key exchange. Okay, so there's no proof that breaking Diffie-Hellman is as hard as computing discrete logs, but nobody knows any other way to break Diffie-Hellman. Okay, so that's why we think it is a reasonable secret sharing scheme. Okay, so now let's see why the discrete logarithm problem is an instance of the hidden subgroup problem. Okay. So again, let capital G be the cyclic subgroup generated by little g, and say that the size of capital G is n. So given some x in capital G, we want to compute the log base g of x. Okay, and we're actually going to formulate this as a hidden subgroup problem in the additive group Zn times Zn. Okay, So this is the group of pairs of elements, A comma B, where both A, B are in Zn, and where addition is just done pairwise modulo n. Okay, so if I have two elements of this group, A comma B and C comma D, I just add them by adding A plus C modulo n in the first coordinate and B plus D modulo n in the second coordinate. Okay, so that's the sum of two elements of the group. Okay, so that's the group that we're going to be working in. Okay, so now we want to define a function f from Zn times Zn to G that is somehow going to encode this value that we're interested in, log base G of x, as a hidden subgroup. Okay, and the definition of f is just going to be the following. So on input A comma B, f is going to be equal to x to the power A times G to the power B. Okay, so that's the definition of f. Okay, so let's take a look at where f is constant. Okay, so first of all, I'm just going to make a common base here. Okay, so x to the power A, I can write that as G to the A times log base G of x. Okay, so that means that x to the A times G to the B is just G to the power A times log base G of x plus B. Okay, so in particular, f is going to be constant when this exponent here takes on the same value modulo n. Okay, why modulo n? Well, because n is the order of g. Remember, that's the definition of n. It's the order of g. So g to the power n is equal to 1. Okay, so adding n to the exponent here doesn't change the value of g to that exponent. Okay, so that means that f is going to be constant on these on the set of the form, the elements a comma b, where a times log g of x plus b is equal to the same value modulo n. Okay, and when this value is c, let's call this set LC. Okay, and now also note that f is distinct on different sets LC and LC prime. Okay, when C is not equal to C prime. Well, why is that? Well, on the set LC, f takes on the value g to the power c. On the set LC prime, f takes on the value g to the c prime. Okay, and since the order of g is capital N, if c and c prime are less than n, then we know that g to the power c is not going to be equal to g to the power c prime. Okay, so now we have our sets here. We have our sets LC. We know that f is constant on each LC, and it takes on distinct values on different, on LC and LC prime. Okay, so now let's just see that these sets are actually cosets of a subgroup. Okay, so the subgroup is just going to be L0. Okay, so so what is L0? Well, it's the set of A comma B where A times log base G of x plus B is equal to 0 modulo n. Okay, so clearly the element 0 comma 0 is in this set, which is the identity element of Zn times Zn. And also we see that every element of the form k comma minus k times log base G of x is going to be in this set, right? Again, just because of the definition here. Okay, so that lets us see that it's actually going to be closed under the group operation, right? Because if I have two elements of this set, so which I give here, then when I add them, it is again going to be of the same form, right? This is again of the same form. Some number t here, and then comma minus that same number t times log base g of x. Okay, and we can also see that it's closed under inverses, right? So the inverse of the element, a generic element of L0, which is k minus k log g of x. So the inverse of this is just minus k, comma, k times log base g of x. Okay, and we can see that this element also satisfies this equation, right? So minus k times log base g of x plus k times log base g of x is equal to 0 modulo n. So this element will also be in L0. Okay, so L0 is closed under inverses. Okay, so therefore L0 is a subgroup, and each LC is just a translate of L0, right? So LC is just a shift of L0 by the element 0, comma c. Okay, so these are cosets of L0. Okay, so this shows that the discrete logarithm problem is an instance of the hidden subgroup problem. Okay, and again, just remember, what is the output in the hidden subgroup problem? Well, it's a generator for the hidden subgroup. And in this case, our hidden subgroup is L0. And a generator for L0, well, it has a generating set of just one element. And from that element, we can derive log base g of x. So for example, a generator of L0 would just be this element here, 1 comma minus log base g of x. And clearly from this element, we can derive log base g of x.